The Lycoming O-360 is a very popular mid-range engine used on a huge variety of light aircraft. It's been in production since 1955 and there are well over 100 different O-360 variants. By the end of this video, you'll be able to tell a lot about each variant just by looking at its name. The standard O-360 produces 180 horsepower, but across the wider 360 series they produce between 145 and 210 horsepower in certified form, and with modifications that can push this up to 225 horsepower. Dry weights for these engines run from roughly 125 kilograms to about 185 kilograms, depending on the exact model and accessories. If you've ever wondered how these differences in horsepower are achieved between different variants from an engineering standpoint, or what exactly the difference between something like this variant and this variant is, then you've clicked on the right video. Before we move on to the intricacies, let's quickly cover the engine's basics. The Lycoming O-360 is a 4-cylinder, horizontally opposed, air-cooled direct drive engine. It has a displacement of 361 cubic inches or 5.9 liters, achieved via a bore of 130 millimeters and a stroke of 111 millimeters. It has 2 valves per cylinder of the overhead valve type, with a camshaft located in the crankcase above and parallel to the crankshaft. The camshaft actuates hydraulic tappets, which operates the valves via pushrods and valve rockers. And that is more or less the only set of properties that all variants have in common. I simply can't mention all the different aircraft that the O-360 family has powered over the years, but the popular ones include the Piper PA-28-180, also known as the Piper Cherokee 180, and later Cessna 172 models, first fitted with a 180 horsepower 360 series engine in the 172 RG in 1980, and then from the 1983 172Q onwards, including the 172R and 172S, also known as the Skyhawk R and Skyhawk SP. It has also powered some light twins like the Piper PA-44 Seminole and the Beechcraft Model 76 Duchess, and some helicopters like the Schweizer 300C and the Enstrom F-28. O-360s have even been used on airboats. And that is just a drop in the bucket of all aircraft the O-360 powers and has powered. The first variant of the O-360 was the O-360-A1A, producing 180 horsepower at 2,700 RPM with a compression ratio of 8.5 to 1. It has a full pressure wet sump lubrication system with an engine-driven impeller type oil pump, a system shared by all of the 360 series except one, which we'll get to later. The A1A was first certified in July 1955, and that was the start of a very long line of variants. The prefix variants, or major variants as I like to think of it, are denoted with different prefixes. The O-360 is the standard carbureted 360 series engine, and the HO-360 is the carbureted variant intended for helicopters. The IO-360 is fuel-injected, with most of the fuel-injected 360 series variants using the Bendix RSA fuel injection system. The LIO-360 is the fuel-injected reverse rotation variant for use on twins. The two engines thus spin in opposite directions, which effectively cancels out the usual left-turning tendencies and gets rid of the classical critical engine. So a twin will typically have an IO-360 on one wing and an LIO-360 on the other. Then there's the TIO-360, the fuel-injected and turbocharged variant. Most of the certified models use a TO4 series turbocharger with automatic wastegate control mounted as an integral part of the engine. Another variant is the AIO-360. It's fuel injected, as we can by now tell from the I, but the A denotes that it's set up for aerobatic flying. It has a dry sump lubrication system with an external oil tank and dual scavenge pumps mounted on the accessory housing instead of the normal wet sump on the bottom of the crankcase that all the other variants use. Lastly, we have the AEI-O-360, which can easily be confused with the AI-O-360, but is distinctly different. The AEI-O is also set up for aerobatics, but it does not use a full dry sump system. It keeps the wet sump and adds a bolt-on inverted flight oil system kit. It allows inverted flight via a weighted ball valve system. In normal flight, the breather port vents blow-by gases, but in inverted flight that port becomes the oil supply path to the pump, and vice versa, as illustrated in the operator's manual. I don't want to spend too much time on this, as we still have a lot to cover. Broadly speaking, those are the different prefix variants, so let's move on to the suffix variants, which we'll cover in a bit more detail. After the O360 tag, a range of numbers and letters make up a suffix. Nearly all of these are meaningful in denoting the exact design and specifications of a particular engine. And after this video, you should be able to tell a whole lot about an engine just based on the suffix, because there is some method to the madness. For example, the second character denotes the provisions for propellers. The number 1 indicates provisions for a controllable pitch propeller and 2 does not. So all variants with a 2 as the second suffix character will have a fixed pitch propeller. The number 3 as the second character denotes special length bushings in the propeller flange, though this does not seem to carry over to the IO series. 4 denotes that the engine is using a stiffer or solid crankshaft. The reason I started with the second character is because the first is a bit less precise. A as the first suffix character denotes that it uses a dynafocal mount. B indicates that it also uses a dynafocal mount, but the engine has a lower compression ratio. C denotes conical mounts as well as D, but D also indicates a lower compression ratio. E denotes the 76 series engines, which has a higher compression ratio. The third letter indicates further, smaller changes, usually to the accessories like magnetos and carburetor. Then the letter D for delta, used as the fourth or fifth letter of the suffix, indicates the engine has a dual magneto in a single housing, as opposed to 2 separate Bendix magnetos. The O360-A1AD is thus exactly the same as the O360-A1A, except for the magnetos. Suffixes with the number 6 as the fourth letter, for example the O360-A1G6, indicate the crankshaft has a pendulum type counterweight system installed. Keep in mind this counterweight system does not address primary or secondary imbalance, but addresses torsional imbalance. I've covered torsional vibration in detail in this video. As already mentioned, the original O360 is the A1A variant, producing 180 horsepower from a dry weight of 132 kilograms. All O360 variants that have a suffix starting with A, C, E, F and G are 180 horsepower engines. Most of these 180 horsepower O360s with a compression ratio of 8.5 to 1 have a minimum fuel requirement of 100 LL. The 76 series engines or O360E variants have a compression ratio of 9.0 to 1 and were designed for 100-130 grade, which is no longer available, but have since gotten approval to run on 100 LL. O360 variants with suffixes starting with B and D have lower compression ratios and are 168 horsepower variants. These can run on 80-87 grade due to their lower compression ratio of 7.2 to 1. But 80-87 has not been available for a long time, and the manual does not allow automotive fuel to be used regardless of octane rating. The lowest power variant is the O360J2A, producing only 145 horsepower with a dry weight of 131 kilograms. Interestingly, the engine has the same bore and stroke as the rest, and 8.5 to 1 compression ratio, same as the 180 horsepower variant. It does have special lightweight cylinders, but that doesn't lower power. It only lowers the max power it's rated for. As explained on the engine's certificate datasheet, the limitation is on throttle setting. At 26.5 inches of manifold pressure, RPM is limited to 2400, and at 2700 RPM, manifold pressure is limited to 24.6 inches. The J2A variant is used on the Robinson R22 Beta 2 helicopter. Let's look at a couple more examples and see if this naming scheme makes sense yet. The O-360-A1A6D, for example, is carbureted, standard compression ratio, dynafocal mount, 180 horsepower, offers provision for a controllable pitch propeller with a counterweighted crankshaft and a dual magneto in a single housing. The O-360-B2E uses a dynafocal mount but has a lower compression ratio as denoted by the B, so produces 180 horsepower at a compression ratio of 8.5 to 1, lower than the base IO model. It also only makes provision for a fixed pitch propeller. I think that's enough examples for now. Let's consider the more powerful variants and how that is achieved. The most powerful certified variant is the TI-O-360-C1A6D at 210 horsepower. From the prefix and suffix we can already tell a few things. Firstly, it's a turbocharged, fuel-injected O-360, makes provision for a controllable pitch propeller, and has the pendulum counterweight system and a dual magneto in a single housing. The C1A6D produces 210 horsepower at 2575 RPM, which is 125 RPM lower than most other O360 variants. It's one of the heaviest variants at 172 kilograms. Compression ratio is 7.3 to 1, lower than the normal 8.5, which makes sense for turbocharged engines which require lower compression ratios to prevent detonation. The magneto timing for most O360 variants is set to spark at 25 degrees before top dead center. The turbocharged C1A6D's timing is retarded to 20 degrees before top dead center. This achieves several things, but two are very important. First, it increases detonation margins. Turbocharged engines force air into the combustion chamber at higher pressure, and that means the intake charge gets hotter. Hotter intake charges push it closer to spontaneous combustion or detonation. It's for the same reason the compression ratio is lower. With ignition happening later in the compression stroke, there is less time for detonation to occur. In addition, when peak combustion occurs, the piston is already further down the cylinder as the combustion gas expands. This not only reduces the tendency to detonate, but lowers cylinder head temperatures. This retarded magneto timing reduces engine thermodynamic efficiency by rejecting more heat energy out the exhaust instead of using it. But on the turbocharged variant, some of that lost energy is utilized by spinning the turbo, which in turn feeds pressurized air into the intake. The same goes for the 200 horsepower TI-O-360-A series variants. Some by now would have thought that I'm forgetting the most powerful variant of the O360, which is the HI-O-360-F1AD at 225 horsepower. But if you take a look in the owner's manual from Lycoming, that variant is specified to produce only 190 horsepower. So where does the 225 horsepower number come from? Well, that is actually a number achieved by installing Enstrom's turbocharging kit for the F1AD, which is specifically done for the Enstrom F28F Falcon and 280L Hawk. It produces 225 horsepower at 3050 RPM at 39 inches of manifold pressure as per the FAA certification datasheet. So while it is mentioned in the type certificate datasheet, I'm on the fence if it should be considered the most powerful O360 variant, as it's only available for the Enstrom helicopter. The next section is the meat of this video. But before that, if you appreciate the work I put into these videos, consider supporting me on Patreon. There's 3 tiers with different benefits, ranging from simply getting access to videos before they are released on YouTube, all the way to voting on which videos I will do next. Links in the video description. I'm also still running the promotion to grow my Patreon community, and my gift to you is free mid-tier membership for 3 months, with zero commitment or expectation to continue if you feel it's not for you. Use this on-screen URL to claim it. There's limited spots available. Going back to the standard non-turbocharged O360 variant that produces 180 horses. How is that 180 horsepower increased for the more powerful variants like the I-O-360-A1A that makes 200 horsepower? The obvious difference between the two is that the latter is fuel injected, but that by itself has virtually no impact on the increase in power, because the fuel-injected I-O-360B, E and F variants also produce only 180 horsepower at the same compression ratio as the carbureted O360-A1A. The 200 horsepower I-O-360-A1A has the same bore and stroke and the same 25 degrees magneto timing. It does have a slightly higher compression ratio, 8.7 instead of 8.5. Many people are quick to credit that extra 20 horsepower to that small compression ratio bump. But there simply isn't 20 horsepower hiding in a 0.2 increase in compression ratio. So where does the rest of that gain come from? An often overlooked clue is in the engine's width. Most 360 series engines are about 848 mm wide, and that includes many of the 180 horsepower fuel-injected variants. The angle valve 200 horsepower engines are wider, around 870 mm, yet we know the piston stroke is exactly the same. That extra width is from changes to the cylinder heads. The standard O360 uses what's usually called a parallel valve cylinder head with a relatively flat-topped combustion chamber. Seen from outside, the intake and exhaust ports are at about the same height and the protruding valve covers are square. On the angle valve cylinder heads, which you see on the 200 horsepower I-O360s, the ports are vertically offset and the valve covers are more trapezoidal in shape. The valves move at an angle or slant to each other. This is possible because it has a domed or hemispherical combustion chamber. This makes more power for several reasons. Firstly, the intake and exhaust paths are straighter with bends at lower angles, which reduces flow losses and makes it easier for the engine to breathe. Second, a domed top allows for larger valves, since it expands the flat top 3-dimensionally outwards, creating a larger top surface area. The intake path is also tuned to improve airflow. All this improves volumetric efficiency. The domed shape also promotes better charge motion and mixing, which helps detonation margins and supports that small compression ratio increase to 8.7 to 1 over the 8.5 to 1 of the parallel valve engines. The domed combustion chamber is also responsible for that increase in compression ratio, since the shape leaves less clearance volume in the combustion chamber at TDC and hence increases the ratio. On top of that, angle valve heads tend to run a bit cooler in operation, partly because of the way the valves are spaced and cooled, which is a nice secondary benefit. Of course, there are downsides too. Angle valve 200 horsepower engines are heavier, typically around 9 to 13 kilograms heavier than a comparable 180 horsepower parallel valve engine. And they are wider and thus don't necessarily fit in a cowling intended for a parallel valve engine. They also cost more to overhaul. So you do get extra power and lower CHTs, but you pay for it in weight, width and, money. The following variants have these angle valve domed chamber cylinder heads. Pause here if you want to take a closer look. The 76 series engines, which are the O360E engines and their LO360E reverse rotation counterparts, were Lycoming's attempt to slightly update their 360 series design in a few specific areas. These engines are laid out quite a bit differently from the more familiar A and C series O360s. As per the engine type certificate datasheet, the E-series incorporates a crankcase with an integral accessories section, a front-mounted fuel pump, an externally mounted oil pump, and revised rocker arms. The D at the end of each O360E model designation indicates that the engine uses a single dual magneto unit instead of two separate magnetos. The operator's manual notes that the valve rockers on these engines are carried on a rocker arm fulcrum, rather than on the full-floating steel rocker shafts used on the conventional O360 variants. All the O360E engines have a higher compression ratio of 9.0 to 1, yet they are still rated at 180 horsepower at 2700 RPM, just like the standard O360-A1A. Interestingly, Lycoming's own performance data show that at 75% power, the E-series consumes about 10.8 gallons per hour, whereas the O360-A1A consumes about 10.5 gallons per hour at the same power setting, which is counterintuitive for the higher compression engine. At 65% power, however, there appears to be a small gain. The 76 series datasheet indicate roughly 8.8 gallons per hour compared to roughly 9.5 gallons per hour for the normal A1A at the same power. Most of the E-series variants were cancelled from the E286 type certificate in May 1978. I've seen comments and posts on forums stating that the H in HO or HIO360 does not stand for helicopter but for horizontal. These engines can certainly be used in fixed-wing experimental aircraft, but they were originally intended for helicopter installations, and the type certificate notes reflect that. Most of the HO and HIO360 variants make their rated power at 2900 RPM rather than the usual 2700 RPM used on most fixed-wing variants. That is clearly faster than any direct drive propeller on these engines would normally run, which makes sense given that the helicopter applications use gearboxes or other transmission arrangements between the engine and rotor. Most HIO360 variants are rated either 180 or 190 horsepower, with compression ratios spanning from 8.0 to 1 up to 10.0 to 1, mainly achieved through different pistons. Some of these use the angle valve cylinder heads, while others retain the parallel valve heads. Perhaps the variant that stands out the most is the HIO360-D1A. It is rated at 190 horsepower at 3200 RPM and has a compression ratio of 10.0 to 1, the highest of any model in the entire 360 engine family. Its dry weight is about 145 kilograms and it uses a different crankshaft with narrow crank pins. It's also the only 360 series variant with a maximum approved oil inlet temperature of 260 degrees Fahrenheit, up from the usual 245 degrees. Helicopter engines face different certification requirements than engines primarily certified for fixed-wing aircraft, typically involving higher power settings for extended periods. This also reflects in the recommended TBOs. The HIO360 series generally carry a 1500 hour TBO, with the G1A as an exception, whereas the IO360 engines without an A, H or T prefix are typically set at 2000 hours, 1/3 higher. Fuel injection first made its way into the Cessna 172 with the IO360L2A in the 172R, which entered production in 1996. On paper, it's a straightforward IO360, but the L2A is rated at only 160 horsepower instead of 180, because its maximum approved engine speed is 2400 RPM rather than the typical 2700. The engine itself was not mechanically derated to enforce this lower limit, and there are no electronic controls that can limit RPM on these installations. Instead, the limitation was achieved via a different propeller. By choosing a fixed pitch prop with more power absorption, primarily via a coarser blade pitch, the engine's speed can't accelerate past about 2400 RPM at full throttle during takeoff. The 2 as the second character in L2A tells you it's a fixed pitch propeller only engine. We also know that horsepower is torque multiplied by RPM. So if you hold torque relatively constant and reduce RPM, you reduce power. The theoretical numbers confirm this exactly. The interesting twist comes from the Cessna 172S or Skyhawk SP, which arrived in 1998. In that model, the exact same I-O-360 L2A installation, with a different propeller, is operated up to 2700 RPM for a rated 180 horsepower, showing that the earlier 2400 RPM limit was not a hard engine limitation. I've seen claims that running the L2A at 2400 RPM improves fuel economy. After all, a lower engine speed would reduce fuel burn, so surely it must be more efficient. But if you look at Lycoming's own data, that's not what the fuel flows show. At 75% power, which is 120 horsepower, the I-O-360 L2A burns about 8.8 gallons per hour, according to the Lycoming charts, while the other 8.5 compression ratio I-O-360 variants burns about 8.5 gallons per hour at 65% power, which is 117 horsepower. Essentially the same output at a lower throttle setting. So at comparable horsepower, the L2A is not actually more efficient in terms of fuel burn. In addition, why is the 172S with its extra 20 horsepower only a few knots faster than the 172R? Firstly, the 172 is a relatively high drag airplane, and increasing power does not result in proportional increases in cruise speed. Secondly, the coarser pitch propeller used to keep the R model's max engine RPM down at 2400 has a side effect. It tends to favor higher cruise speed at the expense of takeoff and climb performance. A propeller with coarser blade angles remains effective at higher air speeds, which helps cruise speed. Clearly, it's not possible to cover over 100 different engine variants in detail in one reasonable length video, but hopefully I've touched on all the most notable variants. If you want to verify anything or dig deeper into a particular variant, it's actually quite easy to look it up yourself. The principal sources are the 3 Lycoming operators manuals for the main O360 variants. In addition, I've used the E286 type certificate datasheet, which covers all the naturally aspirated carbureted 360 series variants, the 1E10T-CDS, which covers the fuel injected variants, and the E16EA-T-CDS for the turbocharged TIO360 models. I've placed links to all of these documents in the video description. Let me know what you thought about this slightly different video. Thanks for watching. Remember to check out the Patreon links below, and I'll see you in the next one.